Yep.
How do you know at first you're reading that when they're talking about the anti-vax movement potentially bringing back smallpox?
Oh yeah.
Yeah.
Yeah. It's almost a stretch. Almost a stretch. But the measles, we've had measles outbreaks in Washington and Oregon.
Yeah, but measles
because that's also
in the population in certain parts of the world. Smallpox is completely eradicated.
I mean, it was. It'll pop back up. I think the different strains. So they transferred over.
I thought smallpox only had humans as reservoirs, and so once we eradicated it, there's no more circulating strains except for what's
naturally occurring was wiped out.
Yeah.
They still have it.
Yeah.
I'm sure it'll it'll escape from a bat population. No. Yeah, I don't know. Smallpox. Yeah, we don't have to do that. Polio is the one that I was thinking of. Polio is definitely, yeah, we kind of basically wiped it out here, but you have other countries where we didn't.
Mostly in the Middle East. But it's like, if you think smallpox is going to come back, people aren't getting vaccinated. You're clearly mistaken, because unless somebody decides that it's a good idea to use a bioterrorism agent, which hopefully they've now seen that seasons go crazy, and it's just not a good idea.
Unless that's their plan. All right, let's see here. So we're checking normality. All of this is in preparation for doing our statistical tests that require normally distributed data. So we ran this to get our yes, no one, and no two. All right, our assessment methods are graphical, or we can run a statistical test. And I've already told you the preferred method is going to be these quantile plots. But I'm going to show you how to do each of these. One, histograms with overlaying a curve could be useful if you're reporting on, let's say, size distributions and you want to overlay some sort of curve on it. So we're going to show you how to do that, and you can learn how to do that curve. The Shapiro-Wilks normality test will learn because if you have a situation where you assess normality and you use a quantile plots, but you have a reviewer that says, well, I need a p-value, well, here's a test that'll assess that'll check normality for you. But definitely, I don't recommend this test. So, histogram method and overlaying a curve. Two-step process. We have to first run our hist function, create the histogram, and we have to remember to do frequency equals false. All right, and then once we create that, we have the curve function where we add a normal curve defined by our own variable mean and our variable standard deviation. We have to make sure we have add equals t so that it adds it right to the graph. And then we saw that we could change it. So I'm going to go back into my R markdown. I'm going to load my car package again. I'm going to run this histogram with the normal curve. So we know that when we run this, this works. And we did do some changes to the graph just to make sure everything fits on here. And I will warn you right now that you can make these changes so that it looks good on here, but then when you knit your document to Word, it's going to change the size of the figure and it could change your scale, so it could look different. Don't panic. All right, I can see what the output is looking like. I can actually read your functions. All right, the code. So if the code's correct, but the figure is just slightly off because of how it was knitted and exported to PDF, you get credit for it. What happens if we change the frequency? So this is going to be the most common mistake, is that you forget to add this frequency equals false. All right, the default is t. All right, so what happens if we did frequency equals t? If you do that, you're going to get, oops, let's take out y lim here. I'm going to do this. Change that to false. I'm going to take the y lim off because this will be the most common situation where you get something like this. So frequency equals t, which is the default, gives you the counts for each of the bins. right? So your y-axis is going to be whole numbers usually. They make it pretty. But then your curve is way down here, and especially if you add a color, you'll be able to see it. Say, oh yeah, why is my curve way down there? Something's wrong. Maybe I screwed up. No, you didn't screw it up. D norm is giving you percentages. D norm is actually giving you a proportion. All right, but we're on the y scale is on the graph, so that is why we use frequency equals false. So as soon as I do that, you see we're now back with proportions. Oops, I have to run that again. Back with proportions, and now our curve fits the graph. So again, the most common mistake that I see, and I bet somebody does this on the exam, prove me wrong. All right, prove me wrong. That you'll get something like this, and you'll be stuck and say, I don't know how to fix that. So I'm gonna down here. So we've got the here. We've got our Y lim and X lim. We've got our colors. All right. But I want to, before that note, I want to specify that frequency equals F. So frequency equals F to make sure the data are graphed as a proportion. I don't want to say frequency because a frequency could be a count or proportion. So value between 0 and 1. All right. The reason is the curve, the denorm part in the curve function returns a proportion or a density. We'll do density. So density that is also between 0 and 1. All right. If we did not include frequency equals F, then the default is frequency equals T, which plots raw counts, and our curve function will add a line that follows the x-axis. So just kind of clarifying why we needed that frequency equals F to get the graphs to appear properly. Are we using this to assess normality? No, the preferred method is the quantile plots. That's going to be the preferred method. But again, if you go out and you sample fish and you measure the fish size, or let's say fish weights, you did fish weights. One of the first steps you do is look at the data. You make a histogram, all right, just to see did you mistype anything? Are we looking at a single peak? All right, does it look skewed? Yes or no? All right, and one of the things we can do when we do those is we can overlay a normal curve. Or perhaps we know that size is skewed. Size of fish and probably weight of fish is skewed due to the changes in age-related mortality, or you could say size-related mortality risk in fish. So we can actually fit, let's say, a negative binomial distribution, or we could fit some other distribution to it and kind of overlay a curve. All right, so that was the histogram. The other one is the quantile plots. This was in the car package, which the new version, I'm not sure if I like it or not. But we have to load the car package, so library car. Right. And then we use QQplot with a capital P. Capital P. Right. Distribution is optional. The default is norm, and since we're always just testing against a normal distribution, we'll just leave it. We'll ignore it. So QQplot of our vector. What we are looking for is obvious curvature, something like we did up here, or an excessive number of points outside of that 95% confidence envelope in both, in one or both of our tails. All right, so in R, I loaded that car library that was at the very beginning, and then we're dealing with our vector, so it's just QQ plot, yes, and note the capital P. If you use lowercase p, I think it complains about it, like you can't find a function. No, sort. Argument Y is missing with no default. Argument Y is missing with no default. So we do this. This is our graph. There's our one-to-one line. This is plotting observed quantiles versus the predicted quantiles based on a normal distribution of the mean of our vector and standard deviation of our vector. So we're looking for points that follow this line that are all inside our confidence envelope, and it looks good. So this looks normally distributed, and it should be. We randomly drew it from a normal distribution. So now I asked you to do the nose. So do the histogram and then do a quantile plot so we can see it. Right? So hopefully you did that. So this will be practice. So we can see what it looks like. So we'll do no one. All right, so hopefully you did this, and I know the code's in the presentation, but we're going to do histogram of our no one. I'm just going to take a look at it, see what it looks like. That's not bad. Let's increase that to 10 and see what that looks like. Didn't change. How about 15? Change that to 15, still didn't change. Let's go up to 20. I don't know, I kind of like the first one better, the default. I think I'm going to go back to it. I think I'm going to leave off the brakes. I think that looks pretty good, but I'm going to go ahead. We have frequency equals F. So now we're back on the density, and then we're going to add our curve. So curve dnorm x. Then we have the mean of no one, and our standard deviation is no one. And then add equals t, and I'm going to do color equals, what does it feel like? Aquamarine, and line weight is 2. I'm going to make it a little bit thicker. So look at that. Not the greatest up here. You can see it. Actually, that's a bad one. I don't even know what red's. Oops. Yeah, just change that to red. So it looks like that. So we know it's not normally distributed. You can see kind of what's happening, right? We should be centered here. It looks like we're centered off to the side. All right. So we've got excess number of points down here. We've got fewer number of points here. And then it looks like we've got some excess in the tails. So I look at this. If I saw the histogram, I wouldn't be surprised if this was non-normal. So the better way is to look at the quantile plot. I'm going to use QQ plot. That's a good abbreviation. So I'm just going to do QQ plot. No. And now you can see our obvious curvature. This is definitely curved up. Not only do we have an excessive number of points in our tails, excessive number of points outside of that envelope in our tails, so you can see we've got a lot of points up here, a lot of points down here, but also these points right here are all outside of our envelope. So remember, it's not just the edges, it's got to be the center of the point, and I think the center of the points are outside. So this is clearly non-normal. We conclude non-normal. And no big surprise. We did F distribution, I think, for this one. Right?
What is the add equals to?
We are adding the curve to the previous graphical device. So, did I define that up here? No, first make the histogram, second add the normal curve. We'll go up the add equals t. We'll add the curve to the previously created graphical device. So just add that in there. And it's not on here, so what I'm going to do is history. Okay, so what I'm going to do is this to show you what's going on. I'm adding these to the console. Okay, so what has happened, every time I made this, it adds it to the plot. So this is in the console window, it's not in the R Markdown. So I'm running histogram curve, plot. Keeps adding it, and every time when I run it, it ran, like histogram created the graphical device. And then if I run the curve, it's going to create another graphical device. But since I add equals t, it says don't create another graphical device, just add it to the one that's already there. So once we do this, this cycles between our graphical devices. So I can go back in history to view different figures that I made if I was doing it in the console or in a regular script window. So if I didn't use that add equals t, run histogram, take that out, that's what I get. So there's nothing there, and it's like, okay, you gave me x, but there's nothing for me to plot, so I'm just going to do basically from 0 to 1 or something like that. And that's how they'll always look. So yeah, the add equals t just adds it right to our last graphical device. All right, so that's no 1. Let's go for no 2, same type of thing. All right, histogram, again, I'm going to make hist of no 2, take a look at it, see what it looks like. There we go. That's looking pretty good. Let's try breaks equals 10. No, not good enough. Let's try 20. 20 is pretty good. I'm going to use 20. I think that looks pretty good. And then I'm going to use curve. So d norm of x, where we have the mean of no 2 and the SD of no 2. So again, we're defining what the mean and standard deviation is of our sample because that's what we're going to assume the normal curve is. Add equals t. Line weight is 2. Color is, we'll use blue for that one. I'm going to run the chunk. Object no 2 is not found. Get our capitalization done. Oops. Not add. Frequency equals f. So I did the same thing. Left it off. I got this. It said, oops, made a mistake. Let's fix it. All right. So here's the situation. I look at this. Looks pretty good, right? It's pretty close. We know we drew it from a t-distribution, right? In theory, it should be not normal. This looks pretty darn good. I'd look at it and say, yeah, it's not too bad. Looks like it follows it. Maybe we have a few more points in the peak than we should. Maybe we have a few less in our shoulders than we should, but it looks pretty good. What does our QQ plot look like? QQ plot, go to. Now we see. So if histogram looks at it and just kind of subjective, we could say, yeah, it's actually looking pretty good. It's not until we look at our QQ plot where we see we have an excessive number of points that are way outside of our line. So we had, I think this was 200. Did we draw 200? 1,000. Yeah, 1,000 data points. Right? That's a lot of points. It's way outside. And it looks like we're outside all the way up until we get to the middle. And then we start to follow a little bit better. And then we drop back outside right up around here. So this is non-normal. We know it's non-normal. It's a t-distribution, but the QQ plot is what really reveals it. So one of the reasons why QQ plot is so good. Questions? So this is the old version. Let's take a look at our options for the QQ plot. So QQ plot. Yep.
So my line is flat. Is there a reason for that?
On the histogram? It is. It is. Were you listening when I... Yeah. That's what I did up here to start. So yours probably looks something like this, where the line's right down at the bottom, right? That's because the default is frequency equals t. You have to make sure you use frequency equals false. Oops. It changes. So your y-axis is probably like whole numbers, 10s, 20s, 30s, 40s, 50s, or hundreds. Is that right? Or your histogram. Yeah. See, these should be decimal. So scroll up to your, you only did his number 2 breaks this one. You need frequency equals f. And then down. And notice how that changed. Now we're in proportions. Because that's what the norm is going to give us. It's going to give us our proportions. So make a note, because that happened. I told you it's going to happen. That's one of the most common mistakes that we see. So make a note, have it. All right. All right, tests, normality test. I don't like it. I don't like presenting it because this test really stinks. Really susceptible to sample sizes. All right, but you might. What's that?
Didn't you start pulling up the...
Oh yeah. I was pulling up the help. Sorry.
Like,
Got sidetracked. All right, QQ plot. We're gonna look at this. We have. Let's look at our options. So there is a groups. That'll be interesting. We'll mess around with that when we get to the ANOVA stuff. Color. Where is our shading? So I can see the lines. So you can change it. Like the default is blue, but we can change it based on the palette. So it looks like it's pulling the color from the car palette. So let's see what the car palette looks like. Car palette. So their colors is black, blue, magenta, cyan, orange, gray, green 3, and then red is last. We can change that order. We can specify what palettes to use if we didn't like the blue in that QQ plot. So if we didn't like this blue, we can fix it. What I'm looking for is the shading. There should be an option that allows you to take off that shading. And I just don't see it. Formula, layout, glab, grouping variable, envelope, true. Yeah. So, well, we can mess around with it on Monday if we need to. Envelope. Oh. It's a Yes, so we can specify it here, right here. And it takes a list. I wonder if we could do this. Let's try it. So if we do PQ plot envelope equals. Let's try this. Style equals lines. Let's see what that does. Oh yeah, there it goes. See it? Took out the shading. I wonder what the none is. No envelope. That's a big surprise. So lines. We can change the color. Ooh. Color equals red. That didn't work. Ooh. Okay. How well? We're not going to worry about the color, but filled. And then we can do alpha. So the default is 0.15. So we'll take a look at that again. So that's 0.15. If we go to 0.5, it should really make it darker. If we go to 0.05, make it smaller, it should become lighter shading. So. Yep. Yeah. If you need to do this, oh, border. Yeah, I don't like border. Because border equals false. Oh, look at that. Now you can really, now we can change it back to the default. That's a little bit better. Now we got actually just shading in here instead of lines that outline it. If you need to have this and you need to update it for something, come talk to me. I'll help you out. So there's a lot of things that we can edit. That's pretty cool. All right, let's move on. So normality test. This test looks at normality. And the Shapiro Wilks test, what it's going to do is look at skew, and it's going to look at kurtosis. So if we violate skew, right, we're non-normal. If we violate kurtosis, we're non-normal. If we violate both, we're non-normal. All right, so it's going to look at both. It doesn't tell us if we're skewed or kurtotic or anything. It just says, hey, we're non-normal. All right, so what it's going to do is it fits the observed data to what would be predicted based on the normal distribution. And it comes up with a test statistic. So the farther away we are from normality, the smaller that value is. And then we can kind of look at it based on sample size. How far away are we allowed to be and still be within the realm of possibilities just due to random chance of our samples. All right, and that's the basis for the Shapiro normality test. We access it using Shapiro.test. So Shapiro.test and then our vector. All right, it has to be a vector that we give. We haven't introduced p-values. We haven't talked about how we come up with those p-values yet. So at this point, we're just memorizing. And it's a good thing to memorize the interpretation of the p-values because we're going to work with it moving forward. So if we get a p-value less than or greater, or less than or equal to 0.05, then the data are non-normal. Right, and it's 0.05000 all the way up. So if it's 0.051, it's above. If it's 0.0501, it's above. All right, so if it's above that 0.05, data are normal. If it's equal or below this value, it is non-normal. Why is that? Well, it's our null hypothesis. Our null hypothesis assumes that we are normally distributed. That's how we're coming up with this theoretical. Right? Our p-value gives us a probability that we would get our data like as extreme or more extreme, just by chance alone. So we're saying at 5%. If there's a 5% or less chance that we get this just through random sampling, then it's too likely that something other than chance is producing that difference. All right, so just memorize, if it's less than 0.05, the data are non-normal for this test. If it's greater than 0.05, then the data are normally distributed. When we report our test, what we would report is the name of the test. We ran a Shapiro-Wilks test. We would report the test statistic, in this case is W, we'll see it, and then we report the p-value and our conclusion. So here's our Shapiro-Wilk for the yes vector. So this is isn't the only statistical test of normality, but it is the one that's probably the most common. All right, so Shapiro-Wilk normality test, or Shapiro-Wilk test. The function is Shapiro.test with x, where x is our numeric vector. All right, so Shapiro.test, yes vector, going to run that, we get this output. You'll run it, you'll get it. Then what we'll do is we'll kind of add some specifics. The output tells us what test was run. Shapiro-Wilk normality test, great. Most of our tests here will report what test was run. It reports the data set that we used, which was the S vector. And then W, that's our test statistic. All right, W is going to be, if we are normally distributed, perfectly normally distributed, this will be 1.000. Right. As we start adding deviations from normality, this number will get smaller. We're going to report this, we're going to report it to 3 decimal places. And then we have our p-value. All right. What is our interpretation? I'm going to do interpretation or write-up. Is the yes vector normally distributed or not normally distributed? Okay, so it is. It's normally distributed. So we ran a Shapiro-Wilk test. Our test statistic is W, and our p-value is 0.83. And we'll talk about rounding and stuff. But we have to report the name of the test, the test statistic, the p-value, and the interpretation conclusion. There's one more item that we would have to report, and that's degree of freedom. But this test doesn't have a degrees of freedom associated with it, so we don't need to report it.
What is the W?
You can say W is measuring closeness to the theoretical normal distribution. You can go to Shapiro Test. So you can look at the original Fortran code and applied statistics. You can look at the revised one in 1995. No, what is it? Yeah, 82, these two. So this talks about it, and then you can look at those. And that's the nice thing about the help files is if you're unsure about the test, you can always look at the help file, and they usually give citations. But I don't normally use this test. All right, so this was Shapiro-Wilk test. Let's add some more details. So this test compares our observed data to what is predicted based on a normal and mean of the vector the test compares our observed data to what is predicted based on a normal distribution. If p is less than or equal to 0.05, then we conclude that, actually, before we do that, we're going to add this. The null hypothesis is that the data are normally distributed because as we get to our test, as we get to our statistical tests, I always introduce the null hypothesis and the alternate hypotheses. That allows us to better understand where these p-values are coming from. All right, so the null hypothesis of this test is that the data are normally distributed. Alternate is that the data are not normally distributed. So if p-value is less than 0.05, then we conclude that the data are not normally distributed, or non-normally. If our p-value is greater than 0.05, then we conclude that the data are normally distributed. All right. Great summary of our notes of the presentations. And again, with all of our tests that we introduce, we'll do the exact same thing. Give the null hypothesis, the alternate hypothesis, we'll give our interpretation, and we will have an example write-up so that you can see what has to be included when we report our test. So now, go ahead and try it on the no1 and the no2 vector. We know based on QQ plots they should be non-normal. Let's check them out with the Shapiro test. Yep. Yep. Is your number key? So we're going to turn the number lock off, hit the insert, turn it back on. Now, insert. Yeah, on the number pad it's there, but on these keyboards, the insert key is up here. So it's all lowercase. All right, so we have all of them. I'm going to provide a write-up here because, again, as we get to our statistical tests, we're going to have the write-up requirement for it. So the no1 vector is non-normal. So we've got Shapiro test, or Shapiro-Wilk test, and W is 0.890, and our p-value is that less than 0.0001. And we'll talk about rounding. So see lecture on rounding, p-values, and test statistics. Future lecture. So with our test statistics, we'll talk about rounding p-values, rounding test statistics as well. So again, right now, I'm not going to take off for rounding any of the p-values or the test statistics. But do make sure that you are reporting what test was run and the interpretation correctly. All right. So write-up number 2. The note. So I'll write it a little bit differently. So according to the Shapiro-Wilk normality test, the No2 vector is non-normal. And now I can just give the W and the p-value. It's a different option. But again, I hit everything that I needed to. Test statistic, p-value, and my interpretation, or my conclusion. So yeah, you just look at, you run this test, you look at the p-value. If it's less than 0.05, we're non-normal. If it's greater than 0.05, it's normally distributed. Memorize that. All right. All right, so we've got it. So I do have here give an example write-up, right? And I do make the note here: smaller values W indicate departures from normality. The p-value generates the probability that we would get a value like that just from random chance if we actually were normally distributed. So you can see why it's less important of what the value is, because the more data points that we have, the higher the cutoff is for when we reject it. So at like 100 values, our W may be at like 0.9. That's our cutoff. But then at 1,000 values, it might be at 0.95. So we make sure you just look at the p-value for your interpretation. All right, so why don't I recommend Shapiro-Wilk? It is susceptible to sample sizes. The Shapiro-Wilk test is poor anytime we have a sample size of less than 30. Less than 30, you almost will never find non-normal data. Really bad. If you're between 30 and 100, same situation. You might not detect non-normality. And I did a couple simulations of this where I drew data from a Poisson distribution that's non-normal. All right. And when I had, I think 60 points, 60 random data points, I was only detecting non-normality in about 40% of those random data sets. When I upped it to 100, I was getting it about 95% of the time I was detecting non-normality. When you get to 100, 150, 200, 300, it's usually pretty good. All right, that's a suitable sample size where it'll detect it. Whatever you conclude from Shapiro-Wilkes would be supported by the quantile plots. Once you get above 300, now it's going to start detecting very minor differences. And once we start getting minor deviations from normality, you have to think, well, are these minor deviations really affecting the outcome of the statistical test that we're interested in running? So if we wanted to run an ANOVA, how severe is it? How big of a problem would it be if Shapiro-Wilkes says that we're non-normal just because we have, a couple of points that are just outside of those confidence envelopes on a QQ plot? All right, so this Shapiro-Wilkes, and anytime you go less than 30, it's awful. So if you've got a smaller sample size, don't even run Shapiro-Wilkes. Use your quantile plots to check it out. So my recommendation is always to run the quantile plots. Just use that, unless I tell you to run something else. All right, just use your quantile plots. Base your decision on that, and then it's generally accepted by the scientific community. Just across the board, it's accepted. But if you happen to have a reviewer or someone that says, "Hey, you need to report a p-value in order to convince me," then go ahead and run Shapiro-Wilkes test and report the p-value. All right. So here's a summary of the R code. Summary of the R code histogram with adding the overlay. And note I use that here for data, and it's a vector. Right, and I added the line weight and the color so you have it in the handouts. For the QQ plot, we have to first load the car package and then we run the QQ plot. And then for Shapiro test, it's Shapiro.test. Very easy. All right, so we've got some practice. All right, normality.csv. So what I'm going to want you to do is do this for homework. You can keep it in your notes. This file, this RMB file that you're using to take notes for this, do it here because what we'll do on Friday is we'll open this up and we'll look at each of the ones. We'll try to determine if it is, if each of our columns, Q1, Q2, Q3, Q4, all the way up to Q8, if they are normally distributed. All right. I do ask you to do all three. Make a histogram with the overlay, quantile plot, and then Shapiro-Willis normality test. So we can kind of see what the comparisons are between these three methods. Have an answer that if it's normally distributed, and have a pick of which one you think is best, which test you think is best. I do want to note that normality.data, or the CSV file, normalitypractice.csv, you have a range of values, or a range of sample sizes. So you have one that has like 10 data points, another that has 5,000 data points, right? So there's missing data. That means if you do mean of one of those data points that has the NA, it's going to return NA, and thus your histogram, your curve, is going to fail. It won't add a line because it's got the mean is NA and the SD is NA. So don't forget, when you pass mean of your vector, like this, mean normality.data $Q2, on some of those, you'll probably have to do NA.RM equals T. All right? So have this for Friday, and we will walk through it. I don't think your presentation has the all of this stuff on it. So I think it has some of it, but it doesn't have the answers. So we'll go through on Friday. All right?